Welcome, and welcome everyone to Science Society, but of course, a special welcome to you, Andrea. And let me start with a little bit of an overview mm, introduction about you so the audience gets to know you a little bit, and then we'll usually, Victoria, ask a couple of interview questions before we go into your research, your really interesting research, if that's okay with you.
Sure.
Thank you.
Thank you.
Perfect. So Professor Andrea Alou, I hope I'm saying the pronunciation right.
Yes.
Is is best known for discoveries in invisibility cloaking, so making objects transparent to incoming microwave signals. He um, he made the first freestanding three-dimensional invisibility cloak, which is so cool. And he also developed the first non-reciprocal acoustic circulator or one-way sound device. And Professor Alu's discoveries in metamaterials and plasmonics have broad implications for a range of sectors, including defense, communication, medical imaging, acoustics, mechanics, and robotics. He joined the CUNY and the Advanced Science Research Center from the University of Texas at Austin, where he was a Temple Foundation endowed professor and the Cochrane School of Engineering, and he is a recipient of the Ellen T. Waterman Award from the National Science Foundation, which is one of the top prizes for scientists and engineers in the U.S. And he has been nominated various times and named as finalist for the Blavatnik National Awards for Young Scientists. The world's largest unrestricted prizes for early career scientists. And
I
he,
actually won it
yeah.
last year.
Oh, you won it! Oh, congratulations! I'm so sorry, I didn't.
I guess the bio
Oh
is old.
wow! Oh, that's amazing. And he holds more than a dozen of patents and patent applications, and has co-authored more than 500 highly cited contribution to the scientific literature. Um, it's such an honor having you here for many, many reasons, and for taking the time to come here on such short notice. We really appreciate it. Thank you. I'm handing over.
No, thank you. Thanks for your interest. Thanks for inviting
Yeah,
me.
and Victoria, yeah, thank you.
All right, thank you. Forgive me, Dr. Alu, Andrea, I have to repeat what Katarina just said. It is such an honor to have you here
Thank
and
you.
fascinating to hear of your accomplishments and all of your work. And I have to say, whenever the question goes around, if you could have a superpower, what would it be? Then mine is always that I wish for the superpower of invisibility. It's so fascinating. So, right on. My question is, I'm curious if you can tell us about where your passion came from. Maybe you can recall some time in your youth where that initial spark for your connection to science developed.
Yeah, no, I was always very curious about how things work, and how fascinated by light actually, and waves in general, radio waves. How very different phenomena to the eyes of a high schooler are like light and radio waves, but they are governed by the same laws, the same physical laws. So I was interested since high school, basically, in these topics, and I studied electromagnetics. I mostly studied theory in Italy, and then when I moved here, I started the professor job in Austin as a theorist, and then moved into experiments, and now we do actually mostly experiments in the lab. We have several labs. It's a really great opportunity here at New York at CUNY with the Dream Lab to explore wave physics, kind of curiosity driven, basically, trying to see what are the boundaries, how much we can push materials to manipulate sound, light, and radio waves.
Thank you. And can you tell us maybe some of the events that led up to the work that you're going to share with us tonight? Maybe some of the more, what is the word I'm thinking of? Not motivating, but things that propelled what you're going to share that got you here tonight.
Yeah, I think we wanted to talk about the latest paper we published that is about the phenomenon of time reflections, time reversal of electromagnetic waves. And
Yes, please.
yeah, so this is an exciting experiment, exciting result. It's an idea that has been around for many years. The first paper on this topic was published 70 years ago, but no one had observed yet this form of reflections in time of electromagnetic waves. So we were excited to find a way to do it and observe them and demonstrate this phenomenon. And we've been working in this area for a while. We were among the first to work on using time to add a dimension to the way in which engineered materials can manipulate the propagation of electromagnetic waves of light. Typically, our field is the field of metamaterials, is about 25 years old, and it's a field that really exploits nano fabrication, nanostructures, to create new ways of engaging with light using nano-structured materials. Most of what we do is really to structure materials at a very small scale, at the scale of nanometers, like billions of a meter, to change the way in which these materials interact with light signals. But a few years ago, we proposed that using time as an extra dimension, an extra tool to manipulate light waves, is possible to push the boundaries forward. So do things that space alone cannot do. So we showed, for instance, a few years ago that if you change the properties of a material in time with the right pattern, you can actually break the symmetry with which light travels in space. So you can send light signals in one direction, but block it when they come in the opposite direction. Typically, we are used to the fact that if we can see something or someone, they can see us. That's the conventional symmetry with which light signals travel in space. But by changing the materials that carry these signals in time, one can break that symmetry. And so we've been working on these forms of time variations of materials for a while. And we were very curious about what we can do with it. And we were inspired by these old theoretical papers that were talking about time reflections, that basically are the dual phenomenon of a spatial reflection. Spatial reflection is something quite common, is what happens when you see into a mirror. You look at the reflections from the mirror of the light rays that hit your face, and that's what carries the reflected image. But what we've been after is demonstrating that it's possible to create an analogous phenomenon, but in time rather than in space. A mirror is always there in time, but it's fixed. It's a specific location in space. but we built the temporal analog of this. It's a time mirror that is everywhere in space. It's distributed in space, but it happens only in a specific instant in time, and that creates a very unusual phenomenon for light waves, and that's the core of our experiment.
Yeah, thank you so much for sharing that kind of introduction, and we got to know kind of your path a little bit to how you became the scientist you're today. And for everyone, the slide presentation is pinned on top of the room. Also, there are links in the chat. Um, and yeah, if you would like to go over the slides, we'll then ask questions afterwards. Thank you.
Yeah, I'm not sure how does that work.
Oh, so
I
everyone has the slide link, so people will go slide through them themselves. So if you could just mention when you were switching to the next slide, then people know to switch to the next slide.
Okay.
Thank you.
So
Or
no worries.
say the slide number. That can help.
Okay, let me see if I can, because I'm not really able to open it on my phone. I'm not sure if there is a trick, but I will open it on my computer.
Okay, yeah, the link is above our icons. It's Alu PowerPoint. But yeah, maybe usually when I present, I have the slides separate on my computer. So
Okay.
since it's not the screen share, it doesn't matter.
One moment. Okay, actually, anyways, they opened here in the app. So yeah, the first slide shows the comparison between a spatial interface and a temporal interface. Basically, what you see as a diagram here is in the horizontal axis is a spatial coordinate. So think about it as a one-dimensional spatial coordinate, and the vertical axis is time. So the arrows that you see on the left are a light ray, basically, that hits a spatial interface in which the material is changing in space. There is an interface between one material and another. As you see, that the interface is vertical, so this is a space interface. It's basically when a light moves from air to a different material. By the way, I just want to make sure, can you hear me?
Yeah, we
Yeah.
can hear you fine.
Okay, great. When this happens, typically we experience reflections, right? The fact that the medium has changed implies that there is a discontinuity in space that creates reflections. And as I said before, this is the foundations, for instance, of how we see our face in a mirror, or how we hear an echo when we talk in front of an obstacle like a mountain. A time interface is the dual of this phenomenon in time. So as you see on the right, this happens when the medium in which the light ray is traveling, or light signal is traveling, suddenly abruptly changes at an instant in time, but everywhere in space. All of this happens synchronously at the same instant across the entire medium. When this happens, you experience a time reflection. And the time reflection is dual to a space reflection. In a space reflection, the frequency of the signal is conserved, the energy, but the momentum of the wave is flipped. That's how the wave travels backward. At the time reflection, the momentum of the wave is conserved, but you couple two negative frequencies, and the energy of the wave can change, can be amplified or can be suppressed in time, in energy. So in the next slide, you see the duality of this phenomenon, and actually the sketch that you see on the right side is a sketch that kind of tries to summarize the difference between a regular mirror and a time mirror. In a regular mirror, you see your face, and you hear echoes in which the words are repeated in the same order. But at the time mirror, you have two fundamental effects. One is that the wave is time reversed. So in a time mirror, you see the back rather than the front, and you hear the echoes time reversed. And the second effect, as you see from the colors, is that the frequencies of the signals can be largely converted without distortion. So this is sketched as color change. So all the colors of a broadband signal get converted to new colors. And this phenomenon has been theorized long ago, but has been demonstrated only recently in our paper that just came out for photonic, for photons, for light waves. The next slide shows, sorry, these are some animations, but I guess I'm not sure how much you see in terms of animations, but the next slide shows our measurements compared to our modeling. And basically this slide is only there to demonstrate that the material response before and after we switch the material, and I will explain in a moment how we switch it, has a very uniform dispersion. This straight line implies, this is in the diagram, it's called a band diagram. It's a diagram that on the horizontal axis has momentum, on the vertical axis has frequency, shows a straight line that indicates that this material behaves as a homogeneous medium that suddenly changes its index of refraction by a factor of 2. So it's an abrupt change that changes drastically, largely, the material response. And these are really the ingredients to observe time reflections. And that also tells us why it has been difficult to observe them before. I like to spell out again the analogy with the spatial mirror. We see good spatial reflections in a mirror because the mirror is well localized in space. It's a very sharp interface between two media that are very different, typically air and the metal. The metal makes the mirror. That's why we see very strong reflections and we see ourselves very clearly. If the contrast between the two media were less strong, the reflections would be less. If we built a mirror using glass, for instance, you would see much less reflections because the material properties between air and glass are much more similar than between air and metal. In the same way, if we did not have this very sharp interface, this very abrupt change in space, then also the reflections would be much more smeared and less sharp. Similarly, to get a strong temporal reflection, you need a large change in the material properties that happens very abruptly in time. And that's what we were able to achieve. And it's something that is very difficult to achieve for light waves because light goes fast and you need to be faster than that in changing the properties. And we can change the properties of a material fast, but the challenge is that typically those changes become very small when you want to be very fast. But the ingredients to get strong time reflections are that you get both fast and large changes in a material. So the first demonstration of a time reflection was achieved a few years ago by the group of Matthias Fink in water waves. So we are familiar with water waves. Water waves go very slow compared to light or electromagnetic waves. And this group was able to show that if you create, for instance, an image, I don't know if you can play the video on the slides, but if you imprint an image on the on a pool, for instance, swimming pool, and then you let it evolve in time, that image gets diffracted away. But by giving a kick to the surface of this water pool, the time reversed waves that come from the time reflection converge back and reform the same image. That was the first demonstration of this phenomenon. And we were able to achieve, and this is the next slide, you see the picture of our experiment and how we implemented it. It's a very long, it's about 6 meters long metal strip that carries electromagnetic waves. It winds around itself to make it longer, and then it's connected to many switches that can be triggered uniformly all together in time, very fast. And these switches connect the metal strip to additional circuit elements that act as reservoir material, reservoir capacitors. That extra material can be connected or disconnected very fast. So the idea we had is that instead of changing the material properties, we can add and subtract material very fast by using switches. That was the breakthrough, to realize those two ingredients of a lot of change and very fast. And in the next slide, you see slide 6, the experiment. What you see on the top left is the measurements at the input port. First, you see the signal, this asymmetric broadband signal that gets it's received after a while at the same port, but time reversed. You see that we send first the small peak and then the large peak, but we receive first the large peak and then the small peak. And the other important feature you see is that the temporal scale is stretched. That's because all the frequencies in the signal have been translated to new frequencies, to lower frequencies because of the switching. Also, the transmitted signal that you see in the bottom is stretched by the same amount, but that one is not time reflected. So you see the small peak first and the large peak next. On the right, we have evaluated experimentally the reflection coefficient in amplitude and phase. We have demonstrated that you have a significant time reflection, and it matches well with the theory, and it is actually flat in frequency. All the frequencies experience the same form of time reflection. That's good news. It's what you expect from this phenomenon. And in the bottom, you also see the frequency conversion, the fact that all the frequencies get uniformly converted to half of the frequency, 50%.
Quick question.
Yes.
So these are surface plasmons.
These are surface waves, are not surface plasmons. The waves are traveling in basically a waveguide. It's a strip line. So it's more similar to the signals that travel on a motherboard, for instance.
Like an antenna, you mean?
Yeah. In some ways, yes, it's like an antenna or a waveguide.
Okay, so it is still, RF frequencies with an electric component and a magnetic component.
Exactly. Yes, these are photons at radio wave frequencies.
Okay, thanks.
No problem. Thanks for the question. Yeah, so slide 7 shows more results in that context, explain better what we are doing, what we are observing. We also show the results both when you open the switches and you close the switches. That demonstrates the dual phenomenon, basically when you, the dual form of interfaces. In one case, you are switching from a material that has a larger impedance to one that has smaller impedance, and vice versa. And in the next slide, by the way, those two effects, of course, in one case half the frequency, in the other case double the frequency across the entire range of frequencies carried by the signal. The phenomenon itself is frequency agnostic. It works for any frequency until an upper cutoff that is determined by how fast the switches are. The next slide, slide 8, shows a well-known phenomenon in space of an anti-reflection. So in many cases, in many applications, you want to avoid the reflections when you enter a new material. And it's well known that the common way of doing that is to coat the interface with a material that has some value of impedance in between the other two materials. The most common approach is called an anti-reflection coating. It's a quarter wave coating. Us and other groups have shown a couple of years ago that it is possible to get an analog of this phenomenon in time by switching twice in a material. And now we had this tool of creating these interfaces, and now basically we wanted to show that the interference of time reflected waves can create this phenomenon of zero reflection at a temporal slab. We have basically this the analog of a spatial slab, but now it's temporal. You see in slide 9 this experiment in which we combine the two time interfaces with a certain delay between them. We can control that delay, and what you see on the right is the measurements as a function of frequency, and you see these typical oscillations. Some frequencies have zero reflections, some frequencies have large reflections. This is typical of what you expect when you have a spatial slab. These are known, if you're familiar with the physics, Fabry-Perot resonances or resonators when they are in time. Here we have something similar in space. As you see, it's a filtering basically of the frequency that comes from the interference between the time reflected signals. And in the bottom plot on the right, you see the variation of the reflection as you change for fixed frequency as you change the duration of the temporal slab. That is the analog of changing the thickness of a slab of a material, but now we are changing the thickness in time. So there is an optimal thickness for which you have zero reflection, and that's what we observed in our experiments. I think I don't think we need to go through all these slides. I think maybe the last thing I want to briefly mention is slide 11. This is something that goes beyond actually the paper we've written. It's a new experiment we've done on the same platform, in which we have shown that these time interfaces can create quite unusual interactions between photons. What do I mean by that? When photons bump against each other, they do not act like objects. Two objects, two balls, for instance, when they bump into each other, typically bounce, right? They have some form of elastic or inelastic collisions that depend on the structure of these objects. Photons actually go through each other. They do not interact. So if you send two light beams against each other, they just go through. They don't bounce off. However, what we showed both theoretically and experimentally is that if you send two photons against each other and you apply a time interface like the one we have in our transmission line metamaterial, as we call it, this loaded transmission line with so many switches, the moment the time interface happens can create a strong collision between photons, and you can create quite unusual effects. You can go from but by choosing the instant in which this time interface happens as a function of the interaction between the two photons, so the moment in which you switch can go from a destructive form of collision in which one of the photons actually disappears to an elastic collision in which the energy is conserved, like two bolts that two billiard balls basically that bump into each other and are reflected back, or a constructive collision in which actually the energy in the two signals gets amplified. So by choosing the moment in which we switch, we apply this sharp transition in the material, you can not only make the photons interact, but also largely change the way in which they interact and go from elastic to inelastic to destructive and constructive form of collision. The energy can be dumped into the time interface or can be extracted by the time interface as a function of the time you choose. And the following slides actually show this phenomenon experimentally and demonstrate that can be used for quite interesting functionalities such as amplifying signals or shape signals. For instance, by choosing the right moment, you can kill some portion of a signal because the photon coming from the opposite side basically completely cancels a portion of the signal that is coming from the opposite direction. The last slide, slide 16, shows kind of a schematic that or a conceptual figure that comes from a recent paper we wrote, like a perspective paper, in which we explain a bit of the vision of where these time interfaces fall within the context of engineered materials I was discussing at the beginning of my talk. Basically, the idea is really to combine spatial interfaces that were very good at patterning spatially, and the temporal interfaces that we just learned how to realize. And combining the two, combining time reflected, spatially reflected signals and their interference, we can open new ways of manipulating light, radio waves, and sound. That's what we are looking at the moment. There is a lot of exciting opportunities that we are discovering as we speak and that we can test in this platform and in other platforms we are working on that can also manipulate larger larger frequencies. I don't know if this was clear. I'm happy to answer more questions or go in more details on the along the slides that I shared.
Yeah, thank you so much. This is really interesting work, and it's really for me. I know you said you mentioned and also in the paper that this theory exists for a long time, but that we reached the point, or you and your lab members reached a point to actually show this. When you talk about, time mirrors, it feels like I'm in a sci-fi movie for me. So, yeah, thank you for sharing this. And um, I wanted to ask, so like for a very broad audience, if you say you have a time mirror basically, and you can show these different effects on the waves. Could you, in theory, let's say, information gets passed on, from A to B? Could you basically go back in time and reread or reread the message. Um, and how long could you, in theory, if that would be possible? I know
Yeah,
it's
no,
a
that's a
very
good
small
question.
scale.
So that's actually a very good question, and it's something that is important to spell out, right? We do couple to negative frequencies, and that's actually the trick. We apply basically a phenomenon known as phase conjugation to all the frequencies involved in the signal, but there is a fundamental difference between a spatial reflection and a temporal reflection that you see it actually in slide 1. And by the way, I just learned, it seems like I can actually share. I don't know, do you see now my presentation?
Yeah, we have your presentation.
Okay,
Yeah.
yeah, I see that I'm sharing it now with the app. But anyways, if you go to slide 1, the there is a fundamental difference between the reflected waves in a spatial interface and in a temporal interface. In a spatial interface, the reflected waves go back in space, stay in the same medium as the impinging waves, the one that come in. In a temporal interface, the reflected waves, this orange line, must be in the future, cannot go back in time. This is because of principle of causality. So you cannot send waves backwards in time. That would violate the causality. You would be able to interfere with the past. But what we do is basically a phenomenon of broadband time reversal and phase conjugation. You play in reverse the wave, but you still play them in the future. You cannot change what happened before, or you cannot predict what's going to happen. So that's a fundamental difference that creates also differences in the way in which the two phenomena work. Right? In the temporal interface, time reflection and time refraction exist in the same medium, whereas in a spatial interface, time reflections interfere with the input wave, whereas refraction are, space refraction are in the new medium.
Okay, so you basically can only go in the future, but
But you
like
play the
yeah.
wave in reverse. So it's a phenomenon known as phase conjugation. Actually, we use this time reversal in computing or in imaging. The challenge is that the way we do it at the moment is very inefficient. Typically, we have to use memory. We have to store a signal, put it in a buffer, reverse it in time, and then play it in reverse. Now, what happens in this material is that this happens naturally. The moment you switch, the wave is played in reverse. Is the positive frequencies are converted to negative frequencies, and that's how you actually create this backward propagation in the new medium that conserves momentum. That's basically what is happening in this time interface.
So you can basically be faster and also skip um, the the parts where you kind of have to store information for a
Exactly.
short time.
There
And
are
this
three
makes
advantages.
yeah.
It's requires much less energy. Converting a signal in digital format, time reverse it and convert it back to analog requires a lot of energy. It is slow and it requires a lot of memory. This phenomenon happens instead naturally in the analog domain just by switching. Very fast, low energy, and without memory requirements. That's
So
yeah.
so you've compared like the energy versus like doing it digitally. I'm wondering what the um, relative ratio or comparison is between the energy that is required to modulate the interfaces versus the photon energy that's being redirected.
Yeah, that's an excellent question. This depends a lot on the platform you use. Our platform is actually extremely energy efficient, and that's one of the reasons why we were able to actually do it. The switching in principle requires zero energy. If you have perfect switches, if there are no imperfections, no non-idealities, no parasitics, switching from very high impedance to very low impedance or vice versa requires zero energy because there is no field in the switch. So this phenomenon in principle requires no energy. Even in practice, in the experiments, requires much less energy than the energy actually carried by the signals. And that's a very important distinction from any other way in which you can achieve time reversal of signals. Going digital requires a lot more energy. Another way in which you can do this form of phase conjugation, but limited to narrow range of frequencies, is to use nonlinear optics, to use mixing between signals. But that also is very energy inefficient. Typically, you require very large pump signals to get phase conjugation to work.
Okay, thank you.
Oh, no, thanks. Great questions.
Yeah, I wanted to ask Kirko, Dr. Shah, and then Akil also joined the stage. If you have questions, please go ahead.
Yeah, thank you so much for your wonderful talk. Maybe two questions I have. One of them is what result you got, for example, if we want to consider changing temperature, specifically when we want to talk about cryo conditioning. It might happen. It's important because if somehow we are thinking about data gathering or conservation, it might matter. And another question I had that was about chirality and the impact of that. Do you have any further information that you can share with us?
Yeah, cryo is both great questions. Thank you. Cryo is an interesting condition to be in. We were talking about ideal switches and ideal responses. One of the challenges or non-idealities of this type of phenomena is thermal loss, thermal phonon, unwanted phonon loss in materials and in the switches. So going into the kind of superconducting regime certainly would help and minimize any unwanted parasitics as you want to do high fidelity type of responses, also with very low energy requirements. But if you're thinking of using thermal effects for the switching, for the changes, then that's not really a good route because those effects are actually slow. So those will not help us in terms of the generating these very sharp, abrupt interfaces in time. For the second question, the chirality, that's a great question too. This type of phenomena that we are showing for now involve only isotropic media, so media that respond in the same way to electric fields that are in different directions. But there has been work, theoretical work, including by our group, in analyzing what happens if we switch chiral or anisotropic or even bianisotropic media. It's limited to theory, but we have been thinking of ways to realize this in our platform, adding some form of chirality means breaking spatial symmetry in the material. We need to do it on a scale that is very dense, and we have achieved this already in these switches, and now we have to come up with a way to break also symmetry that we don't do at the moment in the experiment. But we know that when this happens, you can create even more interesting functionalities. For instance, you can create a different response if your photons have right-handed or left-handed polarization. Right now, the phenomena we showed are independent of the polarization of the signal because of the symmetry. But by breaking symmetry and breaking symmetry while you switch abruptly the properties can induce quite unusual responses. And that's what it's one of the directions we're pursuing at the moment. That's a great question.
So theoretically, if we have two objects, so with considering, for example, using the nanomaterials, still the result, it might be dependent, right?
Sorry, I missed the last sentence
Yeah,
you
you
said.
just explained about chirality, and I was wondering if we have two objects, two separated objects that they have a nanomaterials. For example, we just use the mimicking scenario. So how the result, I mean, what might be the possible result?
Yeah, no, so if we are thinking in the context of time interface, it's not sufficient to have a single object, but if you have an array of objects, like a very dense array of objects that are chiral, there's some asymmetry built in, geometrical asymmetry. And for instance, you can switch for each of these objects at the same time, that asymmetry on and off. For instance, using switches, then something more peculiar will happen to these time reflections. You would have a different form of time reflection if the incoming signals have one polarization, like one-handedness of the polarization of light, or the opposite one. So you could have one time interface. So the same time interface for one polarization could amplify the signals, and from the other could damp the signals, could be filtering polarization as a form as you switch.
And what about dissymmetry?
Sorry?
Mirror, for example, dissymmetry.
You mean for different symmetry? Yeah, that
dissymmetry is not symmetrical, for example.
Yeah,
mirror
absolutely.
Dissymmetry.
Yeah, so chirality is an example of that. And playing with the symmetries, this is actually exactly the type of designs that we've been using for quite a while in the context of spatial metamaterials, right? Playing with symmetry classes, with broken symmetries that are tailored at the nanoscale. We are able to control waves in quite surprising ways. And now we're realizing that we can do these things also in time. So creating these forms of symmetry changes, abrupt symmetry changes, can manipulate light signals in surprising ways. Thank you.
Yeah, Akil, do you have a question? Welcome to the stage.
Hi, Katerina. Nice to meet you. Hi, Andrea. Thank you so much for your wonderful lecture. I have two questions, but I don't know if you guys have time, so I'll ask one, and if time permits, I'll ask another one. So, in light of your groundbreaking work on time reversal and frequency translation using metamaterials, how do you envision overcoming potential limitations and scaling these concepts to achieve practical applications such as ultra-high speed data transmission or dynamic control of wave propagation while addressing concerns about energy efficiency and signal integrity? Thank you.
Already have ongoing experiments in this area. Definitely. So the question is, how can we enhance the performance, both in terms of increasing the frequency, minimizing energy requirements? And there are various directions. I mean, we are looking at much improved switching technologies that can switch much faster than the current switches we use, that are commercial switches, can reach close to terahertz in terms of speeds. And we're also looking at special materials like graphene, 2D materials, polaritons, that are these materials that can can couple strongly light to material resonances, underlying resonances in the structure of the material, like phonons or excitons or other forms of material resonances, and this will help us create very fast changes that can be also strong enough to realize this phenomena in the context of low energy requirements, large frequencies, and efficient forms of phase conjugation and of frequency conversion that we have demonstrated in this proof of concept experiment. So this first demonstration is a proof that this can be done, but certainly the research doesn't stop here. There is a lot still to do to demonstrate. We are also very excited to demonstrate the effect of coupling many of these time interfaces. One interesting direction in this context is the field of time crystals. We are used to what a spatial crystal is, periodic combination of spatial interfaces, but one can also realize with this platform a temporal crystal in which these time interfaces happen periodically over time. And this creates very unusual interactions with localized emitters with specific frequencies, and can control quite drastically the interactions of these time interfaces with electromagnetic waves.
Awesome. Thank you so much. Katerina, can I ask another question if there's time?
Yeah, Andrea, if you're okay with it, for me it's fine. It's more up to you if you have a
Sure.
couple.
Yeah. I'm happy. Yeah.
All right.
All
So
great
Thank
questions.
you.
yeah, so given the recent advancements in the topological photonics and the exploration of exotic topological properties and the metamaterials, how do you foresee the integration of topological concepts with your work on extreme control of light and sound, and also like what new paradigms might emerge from this fusion in terms of wave manipulation, robustness against disorder, and potential applications in areas such as secure communication and quantum information processing? Thank you.
Yeah, great question as well. Yes, you guys are very up to date. Yeah, so there has been a lot of interest in the last years in this field in empowering topological concepts to manipulate waves. Actually, what we discussed about symmetries has really its apex in creating this form of topological order for wave phenomena. And we've been working a lot on the context of spatial interfaces that can create topological effects for photons. Now we are starting to look into ways of using also time and space-time interfaces to achieve manipulation of the topological order of for in metamaterials to manipulate waves, and this really creates beautiful results, beautiful ways of manipulating light, very counterintuitive ways of manipulating light, and also opens to a lot of technologies, provides robustness to the wave manipulation, and so it's a very exciting field, and there is a lot of rich opportunities that we are exploring. It's there is a lot to do both on the theory side and on the application and the experimental side.
Yeah, thank you so much for those interesting questions.
Yeah,
And
thank you so much, Andrea, for your valuable time answering my questions.
Thank you. Thanks for
So
the great question.
quick question. How broadband, or from the opposite perspective, how much do you have to know about in advance about how the incoming light is structured in order for this to work? Have you tested the limits in those regards?
Yeah, certainly. Great question. As I said, the phenomenon is completely frequency agnostic. It works for any signal. So basically, any frequency from DC, from zero frequency, to an upper cutoff that depends on the actual speed of your switch will experience the same time reflection. And that's really the beauty of this result, that is an ultra broadband because of its ultra fast speed, right? The frequency is the Fourier transform of time. So having a delta function in time creates a completely frequency uniform response. So the key to extend the response to higher frequencies is to use faster switches, faster phenomena. I was telling before that a mirror doesn't work anymore if you make it adiabatic, if you make it smeared in space. And this, in the same way, the time mirror has to support a large contrast, but at the same time also has to be very concentrated in time compared to the temporal dynamics of the signal. So the upper cutoff frequency will be determined by the speed of your effect, of your transition. With switches, so using exactly the solution that we came up with, you can achieve probably a speed as fast as hundreds of gigahertz, but not faster. Moving to 2D materials and more sophisticated form, polaritonic materials, can actually give you speeds of modulation that can be in the range of femtoseconds. So you can really push the boundaries much, much faster than what you can do with a switch or a transistor. And this is something we are looking at the moment.
So that's an area of my ignorance. Please give me an example or two of polaritonic materials.
So polaritonic materials are a very hot topic at the moment. I think at the beginning of the talk, someone asked about plasmonic or plasmon polaritons. Those are probably the most popular form of polaritons. So plasmons are electronic oscillations at the interface of a metal with a dielectric like air, and plasmon polaritons are strongly coupled electron oscillations to light. So metallic surfaces can support the strongly localized optical signals that are much more confined than what they can be in a regular material because they strongly couple to electrons. But in the last few years, we have found many other platforms that can support forms of polaritons. Don't need to be coupled to electron oscillations. They can be coupled to electronic transitions in a material. We work a lot with multiple quantum wells, for instance. Phonon polaritons are also very popular at the moment. Gallium oxide, molybdenum trioxide support strongly coupled phonon vibrations in the crystal lattices to light. Also very popular are exciton polaritons that couple light to excitonic transitions, and magnon polaritons is another exciting development, or optomechanical forms of polaritons. So all of these give you the opportunity to get light to interact much more efficiently with the material, and therefore they form an ideal platform to realize time interfaces because they give you strong changes in fast times. And that's what we are exploring at the moment, and not just for this problem, by the way. we've been working on these forms. We call them polaritonic metasurfaces since a few years for many opportunities that they offer for nonlinearities and for frequency transitions and wave manipulation.
That sounds very interesting. I think I'm going to have to do some research.
Thank you. I can share papers if you like on general this topic.
Oh, I would definitely appreciate that. If you have them handy, the way we do that on Clubhouse is to put them in the room chat, which is kind of the word bubble on the lower right hand of the screen, or you can send them to Katerina or to me via my
Yeah,
profile.
excellent. It sounds good.
Thank you.
Thank you.
Yeah, thank you so much. I don't know if anyone has any last questions for Andrea. And then I think we will be closing the room soon. And Andrea, you have been talking for an hour now, so you're probably tired. So, um, yeah, if anyone has any last questions, please go ahead. Victoria, I saw you unmute.
I did. I wanted to thank everyone for coming because these rooms are planned. And Katarina, thank you for inviting our fascinating guests. Andrea, thank you for everything that you've shared with us tonight. We have this unpredictability element of the rooms where we don't know who's going to be able to make it or what questions anybody's going to ask. And I think that drives part of the fun. So I want to thank everybody who's here for showing up because you help make these rooms as wonderful as they are. And Andrea, thank you for your
Thank
time.
you. Thanks for the interest and the great questions. It was great discussion.
Yeah, thank you so much. And yeah, we really appreciate it that you came on such short notice. I didn't want to miss the opportunity again.
Thank
But
you. Thank you. No, this is great. Yeah. By the way, are you all based in New York or this is actually more?
no, it's really international. So Victoria is on the West Coast, and Eli, I'm not sure where you are right now.
Los Angeles.
Okay, yeah, and Kirko is on the East Coast in the South in Florida, as far as I know, and I'm in New York. Akil, I'm not sure where you are, but we also have people from different parts of Europe and Asia that come here, Australia. So yeah, so that's why we record also the rooms. Akil, yeah, go ahead.
I said I'm from Mumbai, India.
Yeah, so that's
Okay.
why we do these recordings so people can then later on listen. And the good thing about the Clubhouse recordings is that the chat and also the links we share, they are still active later on in the replay. So whatever we share here. Oh yeah, Frank is in Germany and it's 5 a.m. Oh my God, Frank, thanks for coming. So yeah, so yeah, it's a really interesting community because of that. And depending on the time we do these rooms, it depends on who is live there to ask questions. And some people also send me questions then for these events if they cannot make it. So yeah, thank you for making it.
Great.
Through
Thank you.
through the pandemic, when everybody was stuck at home, Clubhouse was kind of like the really cool international conference that just keeps going.
Great. Yeah, yeah. No, I didn't know about this, and I'm learning now about the app. I just installed it, and I didn't know even what to expect. But this has been great. Thank you.
Yeah, that's really wonderful to hear that you enjoyed it and that it was worth the trouble. I hope
Absolutely.
so. Maybe you come back again. I know your productivity, additionally to your very cool research, is amazing. So we will for sure follow your work and hopefully we'll stay in touch and hopefully I hear you and everyone back soon again. So thank you so much, everyone.
Great. Thank you. Thanks, everyone.
Have a good
Thanks,
night.
Andreas.
See you soon.
And yeah, and if you are interested, the next room will already be tomorrow with Dr. Klein and also his postdoc, Dr. David Castillo, and they will talk about how stem cells have kind of mechanisms to decide if they will die or regenerate, and they discovered this. So it will be really interesting in the future for tissue repair and so on. So yeah, if you're interested in that, feel free to come back. And thank you, everyone. Enjoy your day or middle of the night or wherever you are. And I hope I hear you all back soon.
Thank you. Bye, everyone.
Bye. 3, 2, 1. I'll close the room. Bye.